Sanjay Kumar. He completed his BE Civil Engineering from Madurai Kamaraj University. He also pursued his ME Soil Mechanics and Foundation Engineering from Anna University, Chennai. He worked as a designer engineer for 1 year under a structural consultant in Madurai. He is currently working as a faculty member in the Department of Civil Engineering, Tyagarajar College of Engineering, Madurai. He has organized 2 national conferences at TCE in 2010 and 2014. He's also got 3 publications in international journals. He is an A-lead member for the Geotechnical Consultancy at Tyagarajar College of Engineering.
Welcome to UGC lecture series for architecture. The subject name is Mechanics of Structures 1 and we are in unit 4, which is elastic properties of solids. This is lecture number 11. We shall see the contents of this lecture. We will be seeing the definition for longitudinal strain, lateral strain, Poisson's ratio and volumetric strain. Then we will be calculating the volumetric strain of a rectangular bar subjected to an axial force. Finally, we will be seeing example problems involving principle of superposition for calculating deformation and Poisson's ratio. We shall see the definition for longitudinal strain. Now, this can be explained with the help of this figure. Let us consider a circular bar. Let L be the length of the circular bar and its diameter be small d. So, this circular bar is subjected to a tensile force of magnitude capital P. So, this circular bar will undergo elongation after the application of the tensile force. Now, the length will be increased to L plus additional length delta L. Now, if we consider the lateral dimension, which is the diameter of the bar will decrease. So, the final diameter after elongation will be d minus the decrease in diameter delta d. So, when after the application of this tensile force, length will elongate by an amount of delta L and diameter will decrease by an amount of delta d. Now, we shall see the definition for longitudinal strain. It is a deformation per unit length in the direction of the applied force. Deformation per unit length is nothing but change in length delta L divided by original length L of the bar upon the application of the force P, which is in the direction of force P also. So, the deformation per unit length which occurs along the direction of the applied force is known as longitudinal strain, or it can also be called as primary strain, or sometimes we can also call it as linear strain. So, it is change in length divided by original length of the bar along the direction of the applied force. Since it is a strain, it does not have any unit. Now, let us see the definition for lateral strain. It is a strain which occurs in every direction at right angles to the direction of the longitudinal strain. Now, for the same steel bar, the lateral strain is calculated as delta d divided by small d, where delta d is the decrease in diameter or change in diameter, d is the original diameter. So, this lateral strain occurs at the other direction, which is at right angles to the direction of the longitudinal strain. So, this is the bar, this is the direction of the applied force. Longitudinal strain occurs along the direction of the applied force, that is in x direction, whereas the lateral strain occurs perpendicular to the direction of longitudinal strain. So, lateral strain occurs perpendicular to x direction, which is the direction of application of force. So, lateral strain occurs perpendicular to x axis, which is y axis. It also has no units. Now, we shall see the definition for Poisson's ratio. Within elastic limit, the ratio of lateral strain to longitudinal strain will be a constant known as Poisson's ratio. So, the ratio of lateral strain to the longitudinal strain within elastic limit will be a constant. This constant is known as Poisson's ratio. Generally for metals, Poisson's ratio varies between 0.25 and 0.42. For rubber, which is a pure elastic material, Poisson's ratio varies between 0.45 and 0.5. Rubber has higher Poisson's ratio when compared to metals because it will undergo large amount of lateral strain upon the application of axial force. Now we shall see one problem. A steel bar 160 centimeter long is acted upon by forces as shown in the figure below. Find the elongation of the bar. Take capital E, which is Young's modulus of elasticity, capital E equal to 2.1 into 10 power 6 kg per centimeter square. Now here a steel bar is shown. It does not have uniform diameter throughout its length. The bar has different diameters at different segments or different portions. Also, if you see this figure, the bar is not only subjected to forces at their ends. In addition to these two forces at the ends of the bar, we have forces acting on intermediate locations of the bar. So, this 410 force and this 610 force are acting at intermediate section B and C of this steel bar. Now, we are asked to determine the total elongation of this bar. For this, we are going to apply a principle known as principle of superposition. We are going to divide this given bar into segments of different lengths. That is, we are going to divide segment AB, segment BC and segment CD separately. So, each and every divided segment will be considered as a separate free body. The forces will be split up and then the final deformation will be the algebraic sum of deformations of all the split up segments. Now, we shall split the bar into different segments. So, this is segment AB. Now, this segment AB has a diameter of 3 centimeter. So, basically this bar is a circular bar. So, this is end A and this is the end B of this particular segment. At the end A, which is the free end, we have a force of 910 acting towards left. So, for equilibrium of this particular portion, we should have a force of 910 towards right. So, this 910 acts towards left and this 910 acts towards right. Now, this bar will be under equilibrium. Now, let us consider the mid segment, which is segment BC. So, this is the section B and this is the section C or NB and NC. Now, if you see this figure, at this intermediate section B, we have a force of 410 acting towards right. Already for the segment AB, at the end B, we have a force of 910 acting towards right. So, to get a force of 410 acting towards right, at this particular segment, for the segment BC, at the end B, we should apply a force of 5 tons acting towards left. So, if we superimpose these two portions, that is portion AB and BC, if we join these two portions, what will happen? At the junction B, we will have a net force of, so this is 910 towards right, this force is 510 towards left. So, we will have a net force of 410 acting towards right. So, this force will be 510 towards left at the end B. To compensate this, for equilibrium at the end C, we should apply a 510 force towards right. So, we have 510 force towards right. Now, let us come to the final segment, which is segment CD. At the end D, we have a force of 1110. So, for equilibrium of this particular segment CD, at the end C, there should be a force of 1110 towards left. Now, if we superimpose the portions BC and CD, that is, if we join BC and CD, at the junction C, what will happen? these two forces 510 force and 1110 force will overlap with one another. 510 force is acting towards right, 1110 force is acting towards left. So, the net force would be, that is net force at C would be 610 force acting towards left. Now, we have divided the given bar ABCD into segments of 3 different segments, and the forces are split up and written for each and every segments. Now, the total elongation of the bar will be the algebraic sum of elongation of the individual segments. Segment BC has a diameter of 3.5 centimeter and final segment CD has a diameter of 3 centimeter. We know the lengths of the individual segments also from the figure. Now, we shall do the calculation. Total elongation of the bar delta L will be, for the first portion it will be P1 L1 by A1 into E, plus for the second portion it will be P2 L2 divided by A2 into E, plus for the third portion P3 L3 divided by A3 into E. Now, this P1 is the force which is acting on the first portion. Similarly, P2 is the force acting on second portion, P3 is the force acting for the third portion. L1, L2, L3 are the lengths of the portion first, second and third portions respectively. Similarly, A1, A2, A3 are cross section area of first, second and third portions. E is the Young's modulus of elasticity of the steel bar which is constant for the 3 portions. Now, we shall do the substitution. Forces acting on this individual split up portion. For the first portion AB, we have a tensile force of magnitude 910. We shall substitute the force in terms of kg, because Young's modulus of elasticity is given in kg per centimeter square. So, the first force 910 will be 9 into 1000, 9000 kg into length of the first portion which is 50 centimeter divided by area of the first portion. Diameter of the first portion AB is 3 centimeter. So, the area will be pi by 4 into 3 square. Now, E is constant for all the 3 portions. So, we shall take E outside plus P2. P2 is once again 510 tensile force, 510 is 5000 kg into length of the portion, second portion length is 60 centimeter divided by area is pi by 4 into 3.5 square plus load coming for the third portion is also 1110 tensile force. 1110 is 11,000 kg into length of the portion is 50 centimeter divided by area is pi by 4 into 3 square. So, E is taken outside. So, outside the square bracket we will have 1 by E. Now, we shall do the substitution for E. 1 by E, this E is substituted as 2.1 into 10 power 6. So, the final answer will be 0.0822 centimeter. So, this is the total elongation of the bar ABCD. Here positive sign is coming for all the deformations in the 3 portions, because all the 3 portions are subjected to tensile force. If any one of the force is compressive in nature, then we should put negative sign instead of positive sign. We shall see another problem. A metal bar 5 centimeter cross 5 centimeter in section is subjected to an axial compressive load of 400 kilonewton. The contraction of a 20 centimeter gauge length is found to be 0.5 mm and the increase in thickness is 0.04 mm. Find the value of Young's modulus and Poisson's ratio. So, we have a metal bar which is having a square section which is subjected to a axial compressive force of 400 kilonewton. Gauge length of the bar or length of the bar is 20 centimeter So, this is the length, and breadth of the bar is 5 centimeter, which is small b, and finally, the thickness is also 5 centimeter, which is small t. Upon the application of this compressive force, decrease in length is 0.5 mm and the increase in thickness is 0.04 mm. We have to find out the value of Young's modulus capital E and the Poisson's ratio 1 by m. Now, we shall calculate Young's modulus. Young's modulus is the ratio of axial stress to longitudinal strain. Axial stress is the applied compressive force capital B divided by the cross section area. Cross section area is breadth into thickness. So, this is the axial compressive stress divided by longitudinal strain. Longitudinal strain is the change in length divided by original length. So, we shall do the substitution. Axial compressive force capital P is 400 kilonewton. We shall substitute it in newtons. So, 400 into 10 power 3 into, or this equation will become P into L divided by B into T into delta L, that is P divided by B T divided by delta L by L. So, if this is simplified, the equation will be P L divided by B T into L. So, P into L, L is the gauge length which is given as 20 centimeter. We shall substitute it in millimeters. So, 20 centimeter is 200 millimeter divided by B into T. Breadth of the bar is 5 centimeter, which will be in millimeters, it should be in millimeters 50. Similarly, thickness will be 50 mm. So, this is B into T into delta L. Change in length, that is contraction, is given as 0.5 mm. So, if you do the calculation, we will be getting 64 into 10 power 3 Newton per millimeter square. Now, we shall calculate the value of Poisson's ratio. Poisson's ratio is 1 by m, which will be lateral strain by longitudinal strain. Lateral strain is delta D divided by D, delta D divided by D, and longitudinal strain is delta L divided by L. Delta D, actually here it will be, it is not a circular bar, instead it is a rectangular bar. So, delta D by D can be replaced as delta T divided by T. So, you are given with the increase in thickness. Increase in thickness delta T is given as 0.04 divided by original thickness of the bar is 50 mm, this whole divided by decrease in length delta L, decrease in length delta L is 0.5 mm divided by original length, original gauge length is 200. So, from this Poisson's ratio will come as 0.32. So, Young's modulus is 64 into 10 power 3 Newton per mm square and Poisson's ratio will be 0.32. Now, let us see the definition for volumetric strain. It is denoted by the symbol epsilon suffix v. Volumetric strain is a ratio of change in volume, which is delta v, to the original volume, which is v, of a body when it is subjected to external force. So, volumetric strain is change in volume divided by original volume when the material is subjected to some external force. So, once again it does not have any unit. Now, we shall see the expression for determining the volumetric strain of a rectangular bar subjected to an axial force. Let us consider a rectangular bar of length L, breadth small b and thickness equal to small t. Let P be the axial tensile force acting on this rectangular bar. So, this axial tensile force acts along the direction of length, which will be taken as x axis. The dimension B is along y axis and the thickness is along z axis. Because of the application of this axial force P, the length L will elongate by an amount of delta L. So, L increases by delta L, then the breadth B decreases by an amount of delta B. We have already seen that because of the applied tensile force, remember the force is applied along the direction of length. So, the length will increase, the length will start to increase, the other dimensions B and T, breadth and thickness will decrease. So, decrease in the breadth is delta B. Similarly, thickness T will also decrease by an amount of delta T. Now, we shall get the value of longitudinal strain. Longitudinal strain, which is denoted as E suffix x, because the force is acting along the x axis. So, longitudinal strain E x will be given by the axial stress small p divided by Young's modulus of elasticity P, where small p is the stress, which is the axial tensile stress, E is the Young's modulus. Next, we shall calculate the lateral strain along the y direction, that is along y axis E y. Lateral strain taking place along y axis will be change in breadth divided by original breadth, which is delta B divided by original breadth is B. We know that the ratio of lateral strain to longitudinal strain is Poisson's ratio, that is Poisson's ratio 1 by m is lateral strain by the longitudinal strain. Already we have got the value of a longitudinal strain. So, longitudinal strain multiplied by Poisson's ratio will give us the value of lateral strain. So, Poisson's ratio 1 by m into longitudinal strain. Longitudinal strain is epsilon suffix x, which is small p by E. Now, this delta B is decreasing, delta B is decrease in the breadth, and hence we will be putting a minus sign here. So, lateral strain will be on the negative side because delta B is decreasing. So, E y will be minus 1 by m into small p by E. Similarly, the lateral strain along the other axis z axis will be delta t divided by t, which will be given by 1 by m into 1 by m is Poisson's ratio into small p by E, which is the longitudinal strain. Volumetric strain is given by E suffix v. Volumetric strain E v is the sum of strain occurring along the three directions epsilon x plus epsilon y plus epsilon z. So, epsilon x is p by E, small p by E, epsilon y is negative, it is minus small p divided by m e minus small p divided by m e. We can take small p by E outside, small p by E into 1 minus 2 by m. So, this is the expression for volumetric strain epsilon v, which is change in volume by original volume. Now, we shall see the summary of the things which we have learnt in this lecture. We have seen the definition of longitudinal strain, lateral strain, Poisson's ratio and volumetric strain. Also, we have seen the expression for determining volumetric strain of a rectangular bar subjected to an axial force. Finally, we have seen two problems involving the principle of superposition for calculating deformation as well as for calculating the Poisson's ratio. Students can try out the following questions. Define Poisson's ratio. What is the difference between lateral strain and longitudinal strain? Derive an expression for volumetric strain of a rectangular bar subjected to an axial force. With this, we have come to the end of the lecture. Thank you.